Hi, in this video I'm going to show how to detect objects using a region-based convolutional neural network. There are three main ways that the MATLAB Deep Learning Toolbox shows how to detect objects. One of them is basically detecting the presence of the object in the image without telling you where it is. That's the easiest one. The second one is basically detecting the object and telling you where it is using a bounding box, as what is shown in here. And also, final one is semantic segmentation, which is more precise, in which it tells you precisely the category of each pixel in the image. Okay, for this type of detection, detecting with a bounding box, region-based convolutional neural network, I'm gonna do three videos. One of them is using a convolutional neural network made from the scratch, and the second one is going to be using a pre-trained neural network using ResNet, and finally I'm going to use a YOLO network. Okay, to do this example, I'm going to just walk through this example. Just click open live script and that's going to get you there. Once in the example, the first step is to load the data. You can set the temporary directory wherever you want it to be, and that's going to be passed through here. This is where the data is coming from. This is data that's going to contain 10 different categories like a sheep, a airplane, a frog, etc. Okay, so we're going to use this helper function just to get the data. I'm going to just put a quick breakpoint just to show the script, but this is not much important. The output of this is going to be just a set of images and a set of labels. The first step, we're going to first create a convolutional neural network from the scratch, and it's going to be trained. And basically the type of detection that we're going to do in this first network is basically detect an object without telling you where it's going to be. And then we're going to adapt that same trained network to detect an object and tell you where it is with a bounding box. Okay, so let's download the data. And in my case, I already have the data available, so it's not going to go through this. So let's call load the data. Okay, that's going to do some concatenation. It's going to do some reshape permutation, basically pre-process adapt the data to what we need. I'm not going to go much in detail, just data. Okay, so let's just take a look at how the data is. The size is going to be a 32 by 32. So it's going to be small images with 50,000 samples, and the labels, we can take a look at the labels. For example, frog, truck is basic categories. So there are 10 categories. We know that given, and this is going to get the categories, a function to get the categories of all the training labels, which there are only 10. And now let's display 100 of those images just to get a sample of what we have in the data. Okay, so here are the images. We got horses, airplanes, cats, frogs, birds, etc. Okay, now let's create the network. First, let's get the size of the image. We don't care about the sample dimension, just the height, the width, and the channels, very small ones. And then we're gonna put that into an array and then create the deep learning input layer. We can see here that has that size. And then let's create a regular convolutional neural network, which is basically a trio of convolution, ReLU for regularization, and max poly for downsampling with a stride of 2. We're going to use 32 filters for the outputs of all the layers, and we're going to have some padding to keep the size of the image the same because we're going to use a convolution filter size of 5 by 5. Okay, so with that we got the middle layers, and the final layers are the classification layers. We're going to use a fully connected layers, a couple of them. One of them is going to have 64 features followed by a ReLU layer, and then the fully connected layer with 10 categories for classification followed by the softmax and classification. We're going to put all the layers together, and we're going to create a random weights for the second layer. The second layer is the first convolution layer. The first layer is for the inputs. So let's take a look at this. Okay, The size of this is going to be as expected, the geometrical size of the convolution filter and the number of colors, and after that the number of features that's coming out of the first layer. That's expected. Okay. Okay, there's a small trick for visualization of the weights, and this is good to monitor how your neural network is. I'm gonna take the weights, the random weights, initial weights of the first convolution layer, which we just did right now, and I'm gonna put that into a montage uh, because we're gonna contrast this with what we get after training. We're gonna see after training that these weights are gonna make a little bit more sense. Now you see here, this is the initial state, doesn't make much sense, but we're gonna see it at the end of the training, how the weights are gonna resemble something more like patterns for detecting objects in images. Okay, so the training options are a stochastic gradient descent with momentum, momentum with 0.9, initial learning rate 0.001. We're gonna drop each 8 epochs, and square regularization with 40 epochs, and batch size of 120. Okay, nothing out of this world. Okay, so first we're gonna okay, so we have the layers already. We have it here, and we can also use analyze network to take a look at the network. Okay, here it is. We have the input image 32 by 3, and you can see the convolutions keeps the geometric size the same because of the padding. And we have a 5 by 5 kernel window, and then it's downsampled by the max point layers by half, and you do that 3 times, and eventually you get back to a 3 by 3. We have 64 features. Then you have the fully connected layer, and then the classification layer too. Okay, so fine. We have the layers. We have the labels, which is the frog, truck, etc., airplane, and we have the images in here. And the images are nothing but an array. So this train network method is smart enough to be able to accept a data store, which is usually the object that you use for training data in a deep learning toolbox training workflow. But in here, you're just passing an array of 5,000 colored images and labels, as simple as it gets, and is able to handle that as well. And we pass the images, the labels, the layers, and it's gonna train to classify that, but again, without telling you where the object is. And we pass the options. Okay, so let's train it. In the first epoch, you can see that the accuracy is not very low and the accuracy keeps increasing. Let's take a look at how this is leveraging the GPU, and we can see that it's using 12%, which is not bad. It's increasing pretty fast. It's training good, but still it is 40 epochs. It takes a long time, so I'm not gonna run it completely. So I want to create this object, so I'm just gonna load it. It's already trained. It's the same. So it might take maybe 10 or 20 minutes to. It says 30 minutes to complete if you want to do like that. Okay, so we have the object that is trained. Okay, with the input and the classification output. Now let's validate it. And now again, let's take a look at the weights, how they look for the network after the training. So for the same network, for the same convolution layer. So we're gonna rescale it, and we're gonna take a look. And you can see that it doesn't look random anymore as the beginning. We see something like edges in some places. There are different features in each of these boxes. Sometimes colors, you look for colors, edges, etc. in different directions. You can see this horizontal, diagonal, etc. Okay. So now let's classify the images. So we have I think 10,000 images here. Whoops, it's an array, so I think it's better to, yeah, 10,000 images. Okay. So again, I don't like it to show it like this because this is a classify method from the network that takes as an input the test images and it's gonna give you the outputs. So let's take a look, just at three of them. A cat, a sheep, and a sheep. Okay, let's take a look at the test labels to see what is expected. Exactly, so it matches what was expected. So let's try it for the full vector to see the accuracy. And 75%, which is not that bad for a small training set and training time. Okay, so now that we have our convolutional neural network trained to detect objects, now we're going to adapt it to detect stop signs and also tell us where the stop sign is. But for that, we need training data that also has the location of the object. So for that, we have this training set that not only tells us, let's just pick up this. This training set in particular has more than what we need because it has stop signs and also cars, car front and car rear. We are only interested in this, so we're going to filter out the rest. This is the bounding box, and this is the image. Okay, so let's take a peek at that data, and those images are in this folder. So we need this is within the folder of the installation of MATLAB for the computer vision toolbox, and we're going to concatenate this to the whole set. And now we can see here that we have the full path for the images, and we have a summary here. Okay, so let's pick up only these two columns. So now the data that we have is only the bounding boxes for the stop sign and the images. So let's take out the first image, only one, and then use this computer vision toolbox command to insert a rectangle, and this is the bounding box. You can see here stop sign, this is the label and the line width. So let's take a look at how that looks. Okay, so this is the type of data that we're going to feed to retrain the network to be a region-based convolutional neural network. The category and the bounding box. Okay, now let's train it. For the training options, they are a little bit similar to before. We have 128 in mini batch size, a learning rate, we have a drop period and a drop factor, a max epoch, nothing out of this world again. But now, instead of using train network command, we're going to use train region-based CNN object detector. Okay, so this method, this function has some smarts in it. It's going to pick up the data and it's going to know the category from the column name, stop sign. It figures out the category. And then it gets the bounding boxes for this training data, and it's going to pull out some proposed anchors for detecting object. For this type of problem of detecting an object in an image, you need to provide some anchors that are they are like proposals of object sizes that you expect to find the objects in, and those proposed regions are going to be used to match the output, and finally they're going to be adapted to the object found. Okay, so we're going to pass the convolutional neural network that we trained just to detect objects without knowing where they are. We pass the training options, and also these parameters are going to say, okay, if you are 30% or below the proposed range, then you're going to be a negative. If you are above 50% and up to 100%, then you're declared a positive. Okay, so we're going to use this command, and this is going to return us a new network. This is going to be different. And this one is going to not only detect the object, but also tell you the bounding box where the object is. Okay, so let's train it. And the first thing that it's going to try to do is extract the region proposals. I understand that these are the anchors in which are going to be used as templates to find where the object is. Okay, it takes a while, so I'm going to pause. Yeah. Okay, it finds the region proposals, and then it's going to train the neural network for classification of the object. It starts with 67%. This is going to take a while. I'm just going to show maybe the first epoch round. Okay, after 50 iterations, 6 epochs, we get a 98% accuracy. It jumped really high, really fast, and also for the loss, it dropped down significantly. But again, this is gonna take a lot of time, so I'm gonna just cancel it, and I'm gonna load the RCNN, which we don't have right now. I'm just gonna load it, and take a look at it. And this network right here is the network that basically we provided, the one trained from the scratch. And you can see that it inferred a stop sign, and the background is basically everything else. And this is the proposed regions. Okay, so now let's try it out. Okay, let's take an image for a stop sign and then detect it to see how it goes. Again, detect is a method. I don't like to show it like this. So basically the input of this method is the image and the batch size, but it's only one image. So what we're gonna get here is basically the bounding box for the object. It has 99% confidence, and it is a category of a stop sign. So it detected the stop sign in the image. Okay, so let's get the score. This is nonsense because it's only one score, 99%. And also taking the bounding box is nonsense because it's only one. So let's take this label. Is gonna be the annotation that we're gonna insert in the image with this computer vision toolbox function. It's gonna put the bounding box as a rectangle, and also it's gonna put the annotation with 99% confidence, indicating that it's a stop sign that we just found. Okay, this is the test image, and this is gonna be that image that we're gonna display. Okay. So yeah, effectively for that example, it was able to detect with 99% confidence the stop sign. So it is working, the network is working. Okay, and finally, I'm gonna show some debugging tips. For example, if the network is not detecting very accurately, you can take a look at the activation outputs and visualize them to see where it could be going wrong. So again, here's the network. This is the network that we use as the one that we trained from the scratch. So we're gonna look at the 14th layer. We're gonna pass a test image, the same test image of above, and we're gonna provide the network, and we're gonna use the activations method. This instead of returning us the output, the classification output of the network, is gonna return us the output of the 14th layer. So let's do that. It's not a conventional size because it's a mirror layer. So the class names are basically what it's trained for. Stop sign, we saw this already. Okay, so let's take only one sample. Okay, and now let's take the size of the image because we want to overimpose the feature map on top of the test image. So we have to make this the same size as the image, which is 368 by 653. So we're gonna use IM resize to make them both the same size, and then we use the IMFuse IP image processing toolbox function to put the activation values on top of the test image. And once we do that, we can display it with IMShow. And we can see here that the activations went strong on the stop sign, which is good, and it went a little bit on the lights of the car and things like that. And basically you can keep training or improving the neural network configuration to focus more on what it has to focus and not on the other things. Okay, so we basically were able to create a convolutional neural network from the scratch, train it, and adapt it to be able to detect an object and indicate the location of the object. And in the next video, I'm gonna show how to do this with a pre-trained ResNet network and then a YOLO network to solve this same problem of detecting an object, indicating where it is. Thank you very much for watching.